Section 5.5 Fractions and Decimals. In this video we will see the procedure for changing a fraction to a decimal and what makes a decimal a terminating decimal, what makes a decimal a repeating decimal, how to use the repeating bar, and expressions containing both decimals and fractions. When converting a fraction to a decimal, only one of two things can happen. Either the process will terminate, or the decimal representation will begin to repeat a pattern of digits. In each case, the procedure for changing a fraction to a decimal is the same. Changing a fraction to a decimal. To change a fraction to a decimal, divide the numerator by the denominator. Hint, if you first reduce the fraction to lowest terms, the numbers will be smaller, and the division will be a bit easier as a result. Terminating decimals. First reduce the fraction to lowest terms. If the denominator of the resulting fraction is a prime factorization consisting of strictly 2's and or 5's, then the decimal representation will terminate. Example 1. Change 15/48 to a decimal. Solution. First, reduce the fraction to lowest terms. Factor 15 in the numerator to 3 times 5, and factor 48 in the denominator to 3 times 16. Then the 3's will cancel and we're left with 5/16. Next, note that the denominator of 5/16 has prime factorization of 2 4 times. It consists only of 2's. Hence, the decimal representation of 5/16 should terminate. 5 divided by 16. 16 doesn't go into 5, so we'll add a 0. 16 goes into 50 3 times. 3 times 16 is 48. 50 minus 48 is 2. Add another 0. Bring down the 0. 16 goes into 20 one time. 1 times 16 is 16. 20 minus 16 is 4. Add another 0. Bring down the 0. 16 goes into 40 2 times. 2 times 16 is 32. 40 minus 32 is 8. Add a 0 and bring down the 0. 16 goes into 80 5 times. 5 times 16 is 80. 80 minus 80 is 0. The 0 remainder terminates the process. Hence, 5 divided by 16 is a terminating decimal 3,125 10,000ths. Example 2. Change 3 and 7/20 to a decimal. Solution. Note that 7/20 is reduced to lowest terms, and its denominator has prime factorization 2 times 2 times 5. It consists only of 2's and 5's. Hence, the decimal representation of 7/20 should terminate. To divide 7 by 20, we have to add a 0 since 20 doesn't go into 7. 20 goes into 73 times. 3 times 20 is 60. 70 minus 60 is 10. 20 does not go into 10, so we'll add another 0, bring down the 0. 20 goes into 100 5 times. 5 times 20 is 100. 100 minus 100 is 0. The 0 remainder terminates the process, hence 7/20 equals 35 hundredths. Therefore, 3 and 7/20 equals 3 and 35 hundredths. Repeating decimal. First, reduce the fraction to lowest terms. If the prime factorization of the resulting denominator does not consist strictly of 2's and 5's, then the division process will never have a remainder of 0. However, repeated patterns of digits must eventually reveal themselves. Example 3. Change 1/12 to a decimal. Solution. Note that 1/12 is reduced to lowest terms and the denominator has a prime factorization 2 times 2 times 3 that does not consist strictly of 2's and 5's. Hence, the decimal representation of 1/12 will not terminate. We need to carry out the division until a remainder reappears for a second time. This will indicate repetition is beginning. 12 doesn't go into 1 when we divide 1 by 12. So we have to add a 0. 12 doesn't go into 10, so we'll place a 0 in the quotient, add another 0. 12 goes into 100 8 times. 8 times 12 is 96. 100 minus 96 is 4. Add another 0 and bring down the 0. 12 goes into 40 3 times. 3 times 12 is 36. 40 minus 36 is 4. Note the second appearance of 4 as a remainder in the division above. This is an indication that repetition is beginning. However, to be sure, let's carry the division out for a couple more places. So we'll add another 0. Bring down that 0. 12 goes into 40 again 3 times. 3 times 12 is 36. Minus 4. Add another 0. Bring down the 0. 12 times 3 is 36. 40 minus 36 is 4. Note how the remainder 4 repeats over and over in the quotient. Note how the digit 3 repeats over and over. It is pretty evident that if we were to carry out the division a few more places, we would get 1/12 equals 0.8333 and so on. The ellipsis is a symbolic way of saying that the 3 will repeat forever. It is the mathematical equivalent of the word etc. There is an alternative notation to the ellipsis, namely, the bar over the 3 called the repeating bar indicates that the 3 will repeat indefinitely, that is, 0.083 with the bar over the 3 equals 0.08333, etc. Using the repeating bar to use the repeating bar notation, take whatever block of digits are under the repeating bar and duplicate the block of digits infinitely to the right. Thus, for example, 5.345 with the repeating bar over 45 equals 5.3454545, etc. Important observation. Although 0.833 with the repeating bar over 33 will also produce 0.8333, etc. As a rule, we should use as few digits as possible under the repeating bar. Thus, 0.83 with the bar over 3 is preferred over 0.833 with the bar over 33. Example 4. Change 23 over 111 to a decimal. Solution. The denominator of 23 over 111 has prime factorization 3 times 37 and does not consist strictly of 2's and 5's. Hence, the decimal representation will not terminate. We need to perform the division until we spot a repeated remainder. 111 does not go into 23, so we will add a 0. 111 goes into 230 2 times. 2 times 111 is 222. 230 minus 222 is 8. We'll bring down a 0. 111 does not go into 80, so we will place a 0 in the quotient and add another 0. Bring down that 0. 111 goes into 800. 7 times 111 is 777. 800 minus 777 equals 23. Note the return of 23 is a remainder. Thus, the digit pattern in the quotient should start anew, but let's add a few places more to our division to be sure. Aha! Again a remainder of 23. Repetition. At this point, we are confident that 23 over 111 equals 0.207207, etc. Using a repeating bar, this result can be written 23 over 111 equals 0.207, the repeating bar over 207. Expressions containing both decimals and fractions. At this point, we can convert fractions to decimals and vice versa. We can convert decimals to fractions. Therefore, we should be able to evaluate expressions that contain a mixed fraction and decimal numbers. Example 5. Simplify negative 3 over 8 minus 1 and 25 hundredths. Solution. Let's change 1 and 25 hundredths to an improper fraction. 1 and 25 hundredths equals 125 over 100 equals 5 over 4. In the original problem, replace 1 and 25 hundredths with 5 over 4, make equivalent fractions with a common denominator, then subtract. So, replacing 1 and 25 hundredths with 5 over 4, we get negative 3 over 8 minus 5 over 4. The denominators are 8 and 4. The lowest common denominator is 8 since 4 is a factor of 8. So we'll multiply the second fraction by 2 over 2 to get equivalent fraction 10 over 8 with denominator 8. Then, since we have common denominators, we will combine the numerators. Negative 3 plus a negative 10 is negative 13, so the result is negative 13 over 8. Alternate solution. Because negative 3 over 8 is reduced to lowest terms, and 8 equals 2 times 2 times 2 consists only of 2's, the decimal representation of negative 3 over 8 will terminate. So if we divide 3 by 8, we get a terminating decimal 0.375. Hence, negative 3 over 8 equals decimal number negative 0.375. Now replace negative 3 over 8 in the original problem with negative 0.375, then simplify. So negative 3 over 8 minus 1.25 equals negative 0.375 minus 1.25. Change this to subtraction to adding the opposite. Minus 1.25 becomes plus a negative 1.25. Negative 0.375 plus a negative 1.25 equals a negative 1.625. Thus, negative 3 over 8 minus 1.25 equals a negative 1.625. Are they the same? The first method produced negative 13 over 8 as an answer. The second method produced negative 1.625. Are these the same results? One way to find out is to change negative 1.625 to an improper fraction. Negative 1.625 equals negative 1,625 over 1,000. Prime factor the numerator and denominator. So in the numerator, 1,625 equals 5 times 5 times 5 times 13. There should actually only be 3 factors of 5 in the numerator. And the denominator, 1,000 factors into 2 times 2 times 2 times 3 factors of 5. Since they both actually have only 3 factors of 5, those 5's all cancel and we're left with a 13 in the numerator and 3 factors of 2 in the denominator, which is 8. So the result is negative 13 over 8, thus the two answers are the same. Let's look at another example. Example 6. Simplify negative 2 over 3 plus 0.35. Solution. Let's attack this expression by first changing 0.35 or 35 hundredths to a fraction. So we have negative 2 over 3 plus 35 over 100. We can reduce the second fraction, 35 over 100, to lowest terms 7 over 20. And find an LCD to make equivalent fractions. The lowest common denominator for 3 and 20 is 60, so we'll multiply the first fraction by 20 over 20 to get equivalent fraction, negative 40 over 60, and then we'll multiply the second fraction by 3 over 3 to get an equivalent fraction with the denominator 60, which is 21 over 60. Now that we have negative 40 over 60 plus 21 over 60, and like denominators, we can combine our numerators. Negative 40 plus 21 equals a negative 19, so the result is negative 19 over 60. Thus, negative 2 over 3 plus 35 hundredths equals negative 19 over 60. In example 6, we run into trouble if we try to change negative 2 over 3 to a decimal. The decimal representation for negative 2 over 3 is a repeating decimal. The denominator is not made up of only 2's and 5's. Indeed, negative 2 over 3 equals negative 0.6 with the repeating bar over 6. To add negative 0.6 with the repeating bar over 6 and 0.35, we have to align the decimal points and begin adding at the right end. But negative 0.6 has no right end. This observation leads to the following piece of advice. Important observation. When presented with a problem containing both decimals and fractions, if the decimal representation of any fraction repeats, it's best to first change all numbers to fractions, then simplify.